Welcome to Sleepy Science Student, where we explore the cosmos one gentle thought at a time. Tonight, we're going on a slow, peaceful journey into the life and death of stars. Those brilliant points of light that have watched over Earth since long before humans walked upon it. Tonight, we're going on a quiet, contemplative journey into the remarkable life cycle of stars. From their gentle birth in cosmic clouds to their spectacular deaths that seed the universe with the very elements of life itself, we'll drift through billions of years of stellar evolution. It's a story written in light and time, whispered across the vast distances of space. I hope this video isn't too interesting. Though, if it does happen to keep you awake, at least you'll be learning something fascinating about the stars that quietly shine above us every night. You'll discover why you're made of stardust, quite literally. Not the worst way to spend a sleepless night, pondering your cosmic origins while the rest of the world dreams. Before we drift among the stars together, I'd love it if you gave this video a like and maybe even subscribed if you haven't already. It really helps this gentle little channel grow, reaching more curious minds who find comfort in learning about the universe at a pace that lets them breathe. I'd also love to know where you're watching from and what time it is for you right now. Are you tuning in from a cozy bed in Melbourne at midnight, or listening from a couch in Portland at 3 in the afternoon while pretending to work from home? Perhaps you're in Mumbai at dawn, or in London as twilight settles. Let me know in the comments. It's always such a joy to see the sleepy science community scattered gently across the globe, all of us gazing up at the same stars from different corners of our pale blue dot. Now, settle in, get comfortable, adjust your pillow, let your shoulders relax. You don't need to remember any of this. You don't need to take notes or stay alert. Just let the words wash over you like starlight filtering through a gentle night sky. And as we begin this peaceful voyage into the life and death of stars, remember that this video is for educational and relaxation purposes only. It's not intended as medical advice, astrophysical counseling, or a guide to becoming a star yourself, though you're already brilliant just as you are. Ready? Let's begin. The birth of stars, where everything begins. Let's start at the beginning, in the quiet places between the stars. Space, you might think, is empty, a vast void where nothing exists. But space, as it turns out, is anything but empty. Between the glittering points of starlight lie enormous clouds of gas and dust, floating gently through the cosmos like cosmic mist drifting across an endless ocean. These clouds are called nebulae. The word itself is soft, almost a whisper. Nebula, from the Latin for cloud or mist. And that's what they are, in a sense. Imagine the morning fog that settles over a valley, thick and grey and mysterious. Now imagine that fog spanning not just a valley, but distances so vast that light itself takes years to cross from one side to the other. That's a nebula. Within these cosmic clouds, something remarkable is always happening, though it happens so slowly you'd never notice it in a human lifetime. The clouds are made mostly of hydrogen, the simplest, lightest element in the universe. But there's also helium, and traces of heavier elements, and tiny grains of dust no bigger than particles of smoke. All of it drifting, floating, spreading out across the darkness. But here and there, in certain places within the nebula, something begins to change. Perhaps a nearby star explodes, sending shockwaves rippling through space. Perhaps two galaxies collide in the distance, their gravitational dance stirring the gas. Or perhaps, for no obvious reason at all, a region of the cloud begins to collapse under its own weight. Gravity, patient and persistent, starts to pull the gas and dust together. It's a gentle process at first, a bit like watching sand slowly funnel through an hourglass, except this hourglass is measured not in minutes but in millions of years. As the cloud collapses, it begins to spin, slowly at first, then faster, like an ice skater pulling in their arms. The center grows denser, hotter. Particles that were once separated by vast distances now find themselves pressed together, crowding into an ever smaller space. You can think of it a bit like compressing air in a bicycle pump. As you push down on the pump, forcing air into a smaller space, the air heats up. You might even feel the pump grow warm in your hands. The same principle applies here, but on a scale almost impossible to imagine. As the nebula collapses, the center heats up, not just warm, not just hot, but eventually reaching temperatures of millions of degrees. At the heart of this collapsing cloud, something is forming. We call it a protostar. Not quite a star yet, but well on its way. It's like a star in its infancy, still wrapped in the cosmic cocoon of gas and dust from which it's being born. The protostar glows with a dull red light, heated by the energy released as matter continues to fall inward, pulled by gravity's relentless tug. Slowly, over the course of perhaps 50 million years, which is just a blink in cosmic time, the protostar continues to grow. It pulls in more and more material from the surrounding cloud, growing heavier, denser, hotter. The temperature at its core climbs steadily upward, 10,000 degrees, 100,000, 1 million, 10 million. And then, when the core finally reaches about 10 million degrees Celsius, something extraordinary happens. Hydrogen atoms in the core begin to fuse together. Under the extreme heat and pressure, hydrogen nuclei, which normally repel each other, are forced so close together that they merge, creating helium. This is nuclear fusion, the process that powers all stars. And when fusion begins, the protostar becomes a true star. It ignites. It begins to shine with its own light, no longer just glowing from the heat of collapse, but burning with the fire of nuclear reactions at its core. A star is born. And from that moment forward, it enters into a delicate balance, a cosmic dance between two fundamental forces. Gravity wants to crush the star inward, to collapse it down into an infinitely small point. But the energy released by fusion pushes outward, creating pressure that holds the star up against gravity's pull. For billions of years, if the star is like our sun, these two forces will remain in perfect equilibrium. The star will shine steadily, peacefully, converting hydrogen into helium in its core, releasing energy in the form of light and heat. This process of star formation is happening right now, even as you lie here listening to these words. In the Orion Nebula, visible to the naked eye as a fuzzy patch in Orion's sword, thousands of stars are being born. The Eagle Nebula's famous pillars of creation are stellar nurseries, each pillar containing dense knots of gas that will one day become new suns. Across the galaxy, in clouds both near and unimaginably distant, gravity is patiently gathering matter, igniting fusion, bringing new lights into the darkness. But not all stars are born equal. Some protostars gather just enough mass to barely ignite fusion, creating small, cool, red dwarf stars that will burn slowly for trillions of years. Others grow much larger, accumulating 10, 20, even 100 times the mass of our sun. These massive stars will burn hot and bright and fast, living lives measured not in billions but in mere millions of years, like cosmic mayflies. The mass of a star determines almost everything about its life: its color, its temperature, its size, how long it will live, and most importantly, how it will die. It's a bit like genetics for stars. Their birth mass is their cosmic DNA, determining their entire life story from the moment they first begin to shine. And so a star begins its life. From a diffuse cloud of gas drifting through space, gravity has sculpted a sphere of blazing plasma, held together by its own weight, powered by the fusion of hydrogen atoms in its core. It's a process of remarkable elegance. No one designed it. No one planned it. It simply happens, naturally and inevitably, wherever you have enough hydrogen, enough gravity, and enough time. The universe makes stars the way rain makes puddles, not through intention, but through the simple, beautiful unfolding of physical laws. Let's pause for a moment and consider what this means. Every star you see in the night sky was once just a cloud, just gas and dust, drifting and dispersing. And yet, given time, given gravity, that cloud became a sun. It became a source of light and warmth, a beacon in the darkness. Our own sun formed this way, about 4.5 billion years ago, from a cloud not so different from the ones we see today in Orion or the Eagle Nebula. As our sun's birth cloud collapsed, not all of the material fell into the star itself. Some of it remained in orbit, forming a disk of gas and dust around the young sun. And from that disk, over millions of years, small particles stuck together, forming larger and larger clumps, until eventually they became the planets, moons, asteroids, and comets of our solar system. Earth itself is made from the leftovers of the sun's formation, the scraps that didn't quite make it into the star. This is how planetary systems form. Not just ours, but likely most stars with planets, which, as we're discovering, seems to be most stars, period. When a star is born, it often comes with a family, a retinue of worlds that will orbit it for as long as the star continues to shine. Some of these worlds might be barren rocks, others might be gas giants, and perhaps, on a precious few, the conditions might be just right for something extraordinary to happen. Life, consciousness, beings who can look up at their sun and wonder how it came to be. So stars aren't just born, they create. They're not just passive objects shining in space. They're the wombs from which planets emerge, the furnaces that forge the elements, the anchors around which worlds gather. From the moment a star ignites, it becomes more than just a sphere of hot gas. It becomes a possible cradle for life. But we're getting ahead of ourselves. We've watched a star being born, seen the first light of fusion ignite in its core. Now let's drift forward in time and see what happens next. What does a star do with the billions of years of life that stretch out before it? How does it shine? And what, eventually, brings that shining to an end? The fire at the heart. Understanding nuclear fusion. Before we watch a star live its long life on the main sequence, let's take a moment to understand what's really happening at its core. Let's explore nuclear fusion itself, the process that powers every star, that has been lighting the universe for billions of years. And that makes all the complexity of the cosmos possible. Fusion, at its heart, is deceptively simple. Take two atomic nuclei, bring them close enough together. If the conditions are right, hot enough, dense enough, they'll merge into a single, heavier nucleus. In the process, they'll release energy. That's fusion in a nutshell. But of course, the details are far more fascinating than this simple description suggests. Let's start with hydrogen, the simplest element. A hydrogen nucleus is just a single proton. In the core of a star like the Sun, these protons are flying around at tremendous speeds, heated to temperatures of 15 million degrees. At these temperatures, atoms don't exist as atoms anymore. They're completely ionized. The electrons have been stripped away, leaving bare nuclei zipping through a sea of free electrons. Now, here's the problem. Protons are positively charged, and positive charges repel each other. It's called the electromagnetic force, and it's one of the fundamental forces of nature. Two protons pushed together will naturally push apart. It's like trying to push two magnets together with the same poles facing. They resist, they repel, no matter how hard you push. So how does fusion ever happen? How do protons overcome this electromagnetic repulsion? The answer lies in temperature and probability. At 15 million degrees, protons are moving incredibly fast. Some of them are moving so fast that when they collide, they come extremely close together, close enough that another force comes into play. This is the strong nuclear force, and it's aptly named. At very short distances comparable to the size of an atomic nucleus, the strong force is much stronger than electromagnetism. If two protons can get close enough, the strong force takes over, binds them together, and fusion occurs. The problem is getting them that close in the first place. You can think of it as climbing a hill. The electromagnetic repulsion between protons creates what physicists call a Coulomb barrier, an energy hill that the protons have to climb before they can fuse. At the top of the hill, the strong force kicks in and pulls them together. But getting to the top requires energy. It requires speed. It requires temperature. Even at 15 million degrees, most protons don't have enough energy to climb this hill. Most collisions result in the protons just bouncing off each other. But here's where probability and quantum mechanics come into play. Occasionally, rarely, but occasionally, a proton will quantum tunnel through the barrier. It's as if the proton finds a secret shortcut through the hill instead of having to climb over it. Quantum tunneling is one of those phenomena that has no analogy in everyday life. In the quantum world, particles don't have definite positions. They're described by probability waves, and these waves don't completely drop to zero on the other side of a barrier. There's a small but non-zero probability that a particle can appear on the far side of a barrier without ever having had enough energy to go over it. It simply tunnels through. This quantum tunneling is essential for stars. Without it, the sun would need to be much hotter for fusion to occur, perhaps 100 times hotter. But because quantum mechanics allows this tunneling effect, fusion can happen at the relatively cool temperature of 15 million degrees. Cool being relative, of course, but in the context of nuclear physics, 15 million degrees is almost chilly. When two protons do manage to fuse, whether by having enough energy or by quantum tunneling, they create a diproton, which is unstable and usually falls apart immediately. But very occasionally, within a tiny fraction of a second, one of those protons converts into a neutron through a process called beta plus decay. This creates deuterium, a form of hydrogen with one proton and one neutron. This first step, proton-proton fusion to create deuterium, is actually the slowest, the bottleneck of the entire process. It's governed by the weak nuclear force, which is, as its name suggests, weak. On average, a proton in the sun's core will wander around for several billion years before successfully fusing into deuterium. Several billion years. That's how slow this process is. And yet, this slowness is a blessing. It's why the sun shines steadily for billions of years instead of exploding like a bomb. There are so many protons in the sun's core, so many chances for fusion to occur, that even though each individual proton takes billions of years to fuse, trillions upon trillions of fusion reactions are happening every second. The result is a steady, controlled release of energy that has remained remarkably constant for 4.5 billion years. Once deuterium forms, the rest of the process proceeds relatively quickly. The deuterium nucleus fuses with another proton to create helium-3, which has 2 protons and 1 neutron. Then 2 helium-3 nuclei fuse to create regular helium-4, 2 protons and 2 neutrons, while releasing the extra 2 protons back into the mix to potentially start the cycle again. The net result is that 4 hydrogen nuclei combine to create 1 helium nucleus. And here's the crucial part, that helium nucleus weighs slightly less than the 4 hydrogen nuclei that went into making it. About 0.7% of the mass has disappeared. Where did it go? It was converted into energy, according to Einstein's famous equation, E equals mc squared. Let's pause and think about what this equation means. Energy equals mass, times the speed of light squared. The speed of light is a huge number, about 300 million meters per second. Square that and you get an even huger number, about 90 quadrillion. So even a tiny amount of mass, multiplied by this enormous number, becomes a tremendous amount of energy. When you fuse 4 hydrogen atoms into 1 helium atom, you lose about 0.7% of the mass. That might not sound like much, but multiply it by c squared, and you get enough energy to power the sun for 10 billion years. Every second, the sun converts about 4 million tons of mass into energy. 4 million tons. Every second. And it can keep doing this for billions of years because it contains so much hydrogen, about 10 to the power of 57 hydrogen atoms. Think about that for a moment. The sun is converting millions of tons of matter into pure energy every second, and we barely notice. We see it as gentle sunlight, warm, but not overwhelming. It's only by maintaining this enormous distance, 93 million miles, that the sun's output becomes comfortable for life on Earth. Any closer, and we'd be roasted. Any farther, and we'd freeze. This fusion process is not just physics, it's alchemy. It's the transmutation of elements, the very thing medieval alchemists dreamed of but could never achieve. They tried to turn lead into gold. Stars casually turn hydrogen into helium, helium into carbon, carbon into oxygen, all the way up to iron. It's cosmic alchemy, and it happens naturally, inevitably, in the hearts of stars throughout the universe. Different stars fuse different elements depending on their mass and temperature. Small stars, like the Sun, can only fuse hydrogen and helium. More massive stars can fuse progressively heavier elements, carbon, neon, oxygen, silicon, each step requiring higher temperatures and densities. But no star can profitably fuse elements heavier than iron. Iron is the most stable nucleus in the universe. Fusing iron requires energy rather than releasing it, so stars stop there. And that's fusion, the process that powers the stars, lights up galaxies, and makes the universe a place where complexity can exist. Without fusion, the universe would have remained forever cold and dark, nothing but hydrogen and helium drifting through empty space. But because gravity can compress matter to the point where fusion ignites, stars shine, planets form, life emerges, consciousness arises. So when you feel the warmth of sunlight on your face, remember what's happening. You're feeling the result of nuclear fusion, hydrogen atoms fusing into helium 93 million miles away, releasing energy that has traveled for 8 minutes across the void to reach you. You're feeling the strong nuclear force, quantum tunneling, Einstein's E equals mc squared, all wrapped up in the pleasant sensation of a sunny day. With this understanding of fusion, let's now watch a star live its life. Let's see what happens over billions of years as hydrogen slowly, steadily transforms into helium at the star's core. Let's explore the main sequence, the long, peaceful middle age of a star's existence. The main sequence, a star's long, peaceful life. Once a star begins fusing hydrogen in its core, it settles into what astronomers call the main sequence. Don't let the technical term fool you. There's nothing complicated about it. The main sequence is simply the long, stable period of a star's life when it's doing what stars do best, shining steadily, converting hydrogen into helium, maintaining that perfect balance between gravity's inward crush and fusion's outward push. Think of it as a star's middle age, except far longer than any middle age you or I will experience. Our Sun, for instance, has been on the main sequence for about 4.5 billion years. It's expected to remain there for another 5 billion. That's 10 billion years total, a span of time so vast that it contains the entire history of Earth, from its molten beginnings to the present moment, with billions of years still to come. During this time, remarkably little changes. The star shines with a steady, consistent light. It maintains roughly the same size, the same temperature, the same luminosity. To an observer watching from a distance, a main sequence star appears almost static, unchanging. But inside, at the core, profound transformations are taking place. Deep within the star's core, where temperatures reach 15 million degrees or more, hydrogen nuclei are constantly colliding and fusing. Each fusion reaction combines 4 hydrogen nuclei into one helium nucleus. It sounds simple, but the physics is elegant and complex. The helium nucleus produced is slightly less massive than the 4 hydrogen nuclei that went into making it. That missing mass doesn't just disappear, it's converted into energy according to Einstein's famous equation, E equals mc squared. That tiny bit of mass, multiplied by the speed of light squared, becomes an enormous amount of energy. This energy is released as photons, particles of light, that begin a long, slow journey from the core of the star to its surface. And I do mean slow. A photon created at the sun's core doesn't simply zip straight out to space. Instead, It bounces around inside the star, absorbed and re-emitted countless times, zigzagging through the dense plasma in a random walk that can take anywhere from tens of thousands to hundreds of thousands of years. It's a bit like trying to walk through an extremely crowded room where you can only take one step before bumping into someone and having to change direction. You might end up walking a mile just to cross a room that's only 30 feet wide. Photons inside stars face the same problem, except their crowded room is hundreds of thousands of miles across, filled with charged particles that constantly scatter and absorb them. Eventually, though, after their long journey, photons reach the star's surface. From there, they fly freely through space at the speed of light. 8 minutes later, some of them reach Earth, where they warm your skin, power photosynthesis in plants, and paint the sky blue. The light that touches you on a sunny afternoon began its journey at the sun's core long before human beings existed, before Earth's continents took their current shape, before the most recent ice age began and ended. This is the steady work of a main sequence star. Day after day, year after year, for billions of years, it fuses hydrogen into helium, releases energy, and shines. The process is self-regulating in a way that's almost miraculous. If the star's core gets a bit hotter and fusion speeds up, the increased energy pushes outward more strongly, causing the star to expand slightly. This expansion cools the core, slowing fusion back down. If the core cools and fusion slows, gravity compresses the star, heating the core back up. It's a negative feedback loop, a cosmic thermostat that keeps the star stable for eons. But here's the curious thing. Not all main sequence stars age the same way. The speed at which a star burns through its hydrogen fuel depends almost entirely on its mass. And counterintuitively, more massive stars burn through their fuel much faster than smaller ones. It's not a linear relationship. It's exponential. A star 10 times more massive than the Sun doesn't live 10 times less long. It lives 100 times less long. Why? Because a more massive star has a hotter, denser core, where fusion occurs much more rapidly. It's burning brighter, radiating more energy, consuming its hydrogen fuel at a prodigious rate. A star 50 times more massive than the Sun might shine with 1,000,000 times the Sun's luminosity, but it will only survive for a few million years before exhausting its fuel. Compare that to a red dwarf star with just 10% of the Sun's mass. Such a star burns so slowly, so dimly, that it could shine for 1,000,000,000,000 years, far longer than the current age of the universe. This has profound implications. Every red dwarf star that has ever formed is still on the main sequence. Not one has had time to evolve off of it. They'll continue shining, dim but steady, for time spans that make the current age of the cosmos seem like a brief afternoon. Meanwhile, massive stars live fast and die young, blazing brilliantly but briefly across the cosmic stage. Our Sun is somewhere in the middle, not a lightweight like a red dwarf, but not a heavyweight either. It's a perfectly average star, in mass, in temperature, in luminosity. And that ordinariness is, in its own way, special. The Sun will shine long enough for life to evolve, for intelligence to emerge, for civilizations to rise and fall, and perhaps rise again. A more massive star wouldn't give its planets enough time. A less massive one might never produce enough warmth. There's something deeply peaceful about imagining the Sun as it is right now, in this very moment. At its core, fusion continues as it has for billions of years. Hydrogen becomes helium. Energy radiates outward. Light crosses the void to Earth, where it sustains forests and oceans, algae and elephants, you and me. The Sun asks nothing in return. It simply shines, as it always has, as it will continue to do for billions of years to come. But nothing lasts forever, not even stars. Deep in the Sun's core, the hydrogen fuel is slowly being depleted. With each passing second, a little more hydrogen becomes helium. The star doesn't notice yet. There's still so much hydrogen left. But eventually, billions of years from now, the hydrogen in the core will run low. And when that happens, the long, peaceful stability of the main sequence will come to an end. The star will begin to change, to evolve, to grow old. And it's here, in the twilight years of a star's life, that some of the most remarkable phenomena in the universe occur. But before we drift forward to see stars grow old, let's take a moment to understand how astronomers classify stars, how we've learned to read the stories written in starlight, and how different types of stars lead very different lives. But we're not done yet. What happens to the core of the star after the supernova? We briefly mentioned neutron stars. But before we explore those strange objects, let's consider something equally fascinating. What happens when a star almost forms but doesn't quite make it? What about the objects that fall short of igniting fusion? Let's explore the realm of brown dwarfs, the failed stars. Brown dwarfs, the stars that never quite made it. Imagine a cloud of gas collapsing under its own gravity, gathering mass, heating up, following all the steps toward becoming a star. But then, before the core gets hot enough to ignite hydrogen fusion, the collapse stops. The object glows with a dull red heat from the energy of its formation, but it never truly ignites. It's too small, too light, too cool. It's a brown dwarf, neither a star nor a planet, but something in between. Brown dwarfs are fascinating objects, and they challenge our neat categories. They're not massive enough to sustain hydrogen fusion, which is the defining characteristic of a star, but they're too massive to be planets. They typically have between 13 and 80 Jupiter masses, too light to be stars, but much heavier than any planet. They occupy a liminal space in the cosmic hierarchy. The minimum mass needed to ignite hydrogen fusion is about 0.08 solar masses, or roughly 80 Jupiter masses. Below this threshold, the core never gets hot enough. Gravity compresses the object as much as it can, but electron degeneracy pressure, the same quantum pressure that supports white dwarfs, kicks in before fusion temperatures are reached. The brown dwarf is held up not by the outward pressure of fusion, but by quantum mechanics. But brown dwarfs aren't completely inert. Many of them can fuse deuterium, a heavy isotope of hydrogen with one proton and one neutron. Deuterium fuses at lower temperatures than regular hydrogen, so brown dwarfs above about 13 Jupiter masses can briefly fuse their deuterium. This releases some energy, but deuterium is rare. Only about 1 in every 6,000 hydrogen atoms is deuterium. So the fusion doesn't last long, maybe a few million years, and then the deuterium is exhausted. After that, the brown dwarf simply cools. It glows with infrared light, gradually fading over billions of years. Eventually, it becomes a cold, dark object, still massive, still held together by its own gravity, but emitting almost no light at all. It becomes nearly invisible, detectable only by its gravitational influence or by sensitive infrared telescopes. Brown dwarfs are difficult to study because they're so dim. The first one wasn't confirmed until 1995, even though astronomers had predicted their existence for decades. Since then, we've discovered thousands of them, many lurking in the neighborhood of the Sun. Lumen 16, a pair of brown dwarfs just 6 light-years from Earth, is the third closest stellar system to us, yet it wasn't discovered until 2013. What's interesting about brown dwarfs is that they blur the line between stars and planets. The most massive brown dwarfs are more massive than the smallest red dwarf stars. The least massive brown dwarfs are comparable to the heaviest planets. So where do we draw the line? Is it about mass? About whether fusion occurs? About how the object formed? The current definition hinges on deuterium fusion. Objects that can fuse deuterium, those above about 13 Jupiter masses, are considered brown dwarfs. Objects below this threshold are planets. But it's somewhat arbitrary. A 12 Jupiter mass planet and a 14 Jupiter mass brown dwarf aren't fundamentally different in nature. They're just on either side of a threshold we've chosen for classification purposes. Brown dwarfs may also have weather, They have atmospheres, and observations suggest they have clouds, not water clouds like Earth's, but clouds of minerals and complex chemicals. Some brown dwarfs show variations in their infrared emission, which might be caused by storms or cloud patterns moving across their surfaces. It's a strange thought, weather on an object that's not quite a star and not quite a planet, drifting through space, glowing faintly in the infrared. The galaxy might contain billions of brown dwarfs. They're hard to detect, so we don't know exactly how common they are. But some estimates suggest there could be as many brown dwarfs as there are stars. If so, the galaxy is far more crowded than we thought. Between the visible stars, hidden in the darkness, are countless failed stars, cooling slowly, invisible to all but our most sensitive instruments. And then, there are objects even smaller than brown dwarfs. Sub-brown dwarfs, planetary mass objects that formed like stars, from collapsing clouds of gas, but ended up with less than 13 Jupiter masses. They're not massive enough to fuse anything. They never shone at all, except from the heat of their formation. They're free floating worlds, not orbiting any star, drifting alone through the galaxy. These rogue planets or planetary mass objects might be surprisingly common. Simulations of star formation suggest that many low-mass objects are ejected from stellar nurseries during the chaotic early stages of stellar system formation. They're flung out into space, doomed to wander alone forever, illuminated only by the faint glow of the cosmic microwave background, the leftover heat from the Big Bang itself. It's a melancholy fate, but also strangely peaceful. A rogue planet, once ejected from its birth system, will drift through the galaxy for billions of years. It might pass close to other stars occasionally, but it will never be captured by one. It will simply move through the darkness, a silent wanderer, its surface, if it has one, lit only by starlight from afar and the dim glow of the galaxy itself. Brown dwarfs and failed stars remind us that the universe is more complex than our categories suggest. Not everything fits neatly into boxes labeled star or planet. There's a continuum of objects, from massive O-type stars down through brown dwarfs to gas giants to rocky planets, and each type of object has its own story, its own unique properties, its own place in the cosmic ecosystem. So as we explore the life and death of stars, let's remember that not every stellar mass object becomes a star. Some fall short. They almost make it, but not quite, and yet they exist, scattered throughout the galaxy, glowing faintly, cooling slowly, adding to the richness and complexity of the cosmos. They're part of the story too, the story of matter, gravity, and the endless variety of forms that emerge when simple physical laws play out across billions of objects, over billions of years. Now, having explored objects that never quite become stars, let's look at the stars themselves with fresh eyes. Let's see how astronomers classify them, how we've learned to read the stories written in starlight, and how different types of stars lead very different lives. Reading. Starlight. How we classify the stars. Not all stars are the same. That much is obvious just from looking at the night sky. Some stars appear blue-white, others yellow, still others orange or red. Some are bright, some are dim. Some twinkle, though that's actually an atmospheric effect, while others shine steadily. But how do we make sense of this diversity? How do we classify the hundreds of billions of stars in our galaxy alone? The answer begins with light. Stars emit light across many wavelengths, and by carefully analyzing that light, we can learn an enormous amount about a star without ever visiting it. We can determine its temperature, its size, its composition, how old it is, even how it will die, all from light that has traveled across immense distances to reach our telescopes. The most basic classification of stars is by temperature, which corresponds to color. Hot stars appear blue or blue-white. Cooler stars appear yellow, orange, or red. This isn't arbitrary. It's the same principle that makes flames blue when they're hottest and red when they're cooler. It's black-body radiation, and it's one of the fundamental ways matter interacts with light. Astronomers classify stars by their spectral type, using the letters O, B, A, F, G, K, and M. This sequence might seem random, and historically it was, but it's been retained because astronomers are as sentimental as anyone else. Each letter represents a range of temperatures. O stars are the hottest, glowing blue-white at temperatures over 30,000 degrees. M stars are the coolest, red-orange at temperatures below 3,500 degrees. Our Sun is a G-type star, right in the middle of the sequence. It's yellow-white, with a surface temperature of about 5,800 degrees. Not the hottest, not the coolest, perfectly average. And that averageness has implications. G-type stars like the Sun live long enough for life to evolve on their planets, but they're hot enough to provide adequate energy. Too hot, and the star burns out quickly. Too cool, and planets would need to orbit very close to stay warm, which brings its own problems. But spectral type isn't the whole story. Stars of the same temperature can have vastly different sizes. A red giant and a red dwarf might both be M-type stars, both relatively cool, but the giant is hundreds of times larger. To account for this, astronomers also classify stars by luminosity class, how bright they are compared to other stars of the same temperature. The luminosity classes are denoted by Roman numerals. Class 1 stars are supergiants, enormous bloated stars in the late stages of their lives. Class 3 stars are regular giants, and Class 5 stars, where our Sun belongs, are main sequence stars, stars in the prime of their lives, steadily fusing hydrogen in their cores. So the Sun's full classification is G2V, a G-type main sequence star, slightly hotter than average for G stars. Now here's something fascinating. If you plot stars on a graph with temperature on one axis and luminosity on the other, they don't scatter randomly. Instead, they form distinct patterns. This graph is called a Hertzsprung-Russell diagram, named after the two astronomers who independently discovered this relationship in the early 1900s, and it's one of the most important tools in astronomy. On the HR diagram, about 90% of stars fall along a diagonal line called the main sequence. Hot, bright blue stars are at the top left. Cool, dim red stars are at the bottom right. Our Sun is somewhere in the middle. This diagonal line represents stars that are fusing hydrogen in their cores, stars in the stable, long-lived phase of their existence. Above the main sequence, you find giants and supergiants, stars that are cool in temperature but enormously luminous because of their vast size. Below the main sequence, you find white dwarfs, hot but dim because they're so small. The HR diagram is like a map of stellar evolution. Stars are born on the main sequence, live there for most of their lives, and then move off it as they age and die. Let's talk about some of the specific types of stars you might see in the night sky. O and B stars, the hottest, most massive stars, are rare but spectacular. They're bright, blue-white, and short-lived. Rigel in Orion is a B-type supergiant. It's about 40,000 times more luminous than the Sun, glowing brilliant blue-white. But it won't last long. It's already evolved off the main sequence and will likely explode as a supernova within the next few million years. A-type stars like Sirius, the brightest star in our night sky, are hot and white. They live longer than O and B stars, but still burn through their fuel relatively quickly, maybe a billion years or so. F-type stars are slightly cooler, white to yellow-white. Procyon is an example. Then come G-type stars like the Sun, yellow, stable, living for 10 billion years. K-type stars are orange, cooler than the Sun, but still respectable in their output. Epsilon Eridani is a nearby K-type star, slightly smaller and cooler than the Sun. And then there are M-type stars, the red dwarfs. These are the most common stars in the galaxy, making up about 75% of all stars. They're small, cool, dim, and incredibly long-lived. Proxima Centauri, the closest star to Earth after the Sun, is a red dwarf. It's so dim that despite being only 4 light-years away, you need a telescope to see it, but it will outlive the Sun by trillions of years. Red dwarfs burn their hydrogen so slowly that they'll still be shining long after all the other types of stars have burned out and died. In the far future, when the universe is 100 trillion years old, red dwarfs will be the only stars left, the last lights in a darkening cosmos. There's something poignant about that. The flashy, brilliant O and B stars that dominate the night sky now will all be gone relatively quickly. The steady, unremarkable red dwarfs, too dim to see with the naked eye, will endure. It's a cosmic reminder that slow and steady wins the race. Brightness and brilliance are fleeting. Patience and moderation last. Stars also differ in their composition, though not as much as you might think. Stars are mostly hydrogen and helium, typically about 70% hydrogen, 28% helium, and 2% everything else. But that 2% matters. Astronomers call all elements heavier than helium metals, a definition that would horrify a chemist, since it includes carbon, oxygen, nitrogen, and other decidedly non-metallic elements. But in astronomy, if it's not hydrogen or helium, it's a metal. The metal content of a star tells us its age. The very first stars, formed shortly after the Big Bang, contained almost no metals at all, just hydrogen and helium from the primordial universe. These population 3 stars, as they're called, have never been directly observed. They all died billions of years ago. But we know they must have existed because without them, there'd be no source for the first heavy elements. Population 2 stars are old, metal-poor stars formed early in the galaxy's history. You can find them in globular clusters, dense spherical collections of hundreds of thousands of ancient stars. Population 1 stars, like the Sun, are younger and relatively metal-rich, formed from gas that had been enriched by earlier generations of stars. The Sun's 2% of metals might not sound like much, but it's that 2% that allowed Earth to form, that gave us the elements necessary for life. Astronomers can also determine a star's age, size, and mass by studying its light. The light from a star isn't uniform. It contains dark lines where specific wavelengths have been absorbed by elements in the star's atmosphere. These spectral lines are like fingerprints, unique to each element. By analyzing them, we can determine not just what elements are present, but in what quantities and at what temperatures. It's remarkable, really. We can take light that has traveled for years, decades, or even thousands of years, split it into its component colors, and from that, determine the temperature, composition, size, mass, and age of an object so distant we could never hope to visit it. We can know whether a star is approaching or receding from us by the Doppler shift of its spectral lines. We can detect planets orbiting other stars by watching for tiny periodic changes in the star's motion or brightness. The universe is not hiding from us. It's broadcasting information in every direction, encoded in light. All we have to do is look carefully, think clearly, and we can read the stories written in starlight. We can understand how stars work, how they live, how they die, all from the comfort of Earth, 93 million miles from the nearest star. So the next time you look up at the night sky, remember that those points of light carry messages. Each star is telling its story, its temperature, its age, its composition, its fate. Some are young and hot, burning bright but briefly. Others are old and cool, fading slowly but patiently. Some are massive and doomed to die in violence. Others are small and destined to outlast the galaxies themselves. And we, through the careful application of science and mathematics, through centuries of observation and thought, have learned to understand these stories. We've mapped the stars, classified them, understood their nature. We've taken the scattered points of light in the night sky and woven them into a comprehensive narrative of stellar birth, life, and death. It's one of humanity's great achievements, the transformation of random twinkling lights into a detailed understanding of the cosmos. Now, having seen how we classify stars, let's watch what happens when a star grows old. Let's drift forward billions of years and see a star's hydrogen fuel begin to run low. Let's witness the transformation from main sequence star to red giant, one of the most dramatic changes in a star's life cycle. Red giants, when stars grow old. Imagine, if you will, the Sun 5 billion years from now. For 5 billion years, it has been fusing hydrogen in its core, maintaining its size, shining steadily. But now, the hydrogen in the core is nearly gone. What remains is helium, the ash, so to speak, of all those billions of years of fusion. And helium, at the current temperature of the core, does not fuse. It simply accumulates, inert and useless. With no fusion occurring in the core, there's no longer enough outward pressure to balance gravity's inward pull. The core begins to contract. As it does, it heats up, just as a bicycle pump heats up when you compress it. The core doesn't reach the temperatures needed to fuse helium, not yet, but it gets hot enough that the hydrogen in a shell around the core, hydrogen that was previously too cool to fuse, now begins to burn. This is hydrogen shell burning, and it changes everything. The shell burns hydrogen faster and hotter than the core ever did. More energy pours out. This increased energy pushes the outer layers of the star outward. The sun begins to expand. Slowly at first. Then, more rapidly, it swells like a balloon being inflated. Over the course of millions of years, the sun will grow to perhaps 100 times its current size. It will swallow Mercury, then Venus, and possibly Earth itself. But here's the curious thing. As the sun expands, its outer layers cool. The surface temperature drops from about 6,000 degrees to perhaps 3,000 or 4,000. And because it's cooler, the sun's color changes. It shifts from yellow-white to orange to red. It becomes a red giant. The name is apt. Red, because of its cooler surface temperature. Giant, because of its enormous size. If you could see our sun as a red giant from a distance, it would be vast and bloated, glowing with a dull crimson light. Despite its cooler surface, it would be far more luminous than it is now, simply because it has so much more surface area from which to radiate light. You can see red giants in the night sky right now. Betelgeuse, the bright red star marking Orion's shoulder, is a red supergiant, a more massive version of what our sun will become. Aldebaran, the eye of Taurus the bull, is another. These stars are in the twilight of their lives, their cores surrounded by shells of burning hydrogen, their outer layers puffed up to hundreds of times their original size. But the story doesn't end with the star simply expanding. Remember that contracting helium core? It continues to shrink, continues to heat up. The density at the core increases to staggering levels. A teaspoon of core material would weigh tons on Earth. And finally, after millions of years of contraction, the core temperature reaches about 100 million degrees. Hot enough for a new kind of fusion to begin. Helium nuclei, each containing 2 protons and 2 neutrons, begin to fuse together. It takes 3 helium nuclei, fusing almost simultaneously, to create 1 carbon nucleus. This is called the triple alpha process, and it's how carbon, the element that forms the backbone of all life on Earth, comes into existence. Nothing less than the heat and pressure at the core of a dying star can forge it. When helium fusion begins, something dramatic happens. The process is called the helium flash, though flash is relative in cosmic terms. It actually takes a few minutes. The sudden onset of helium fusion releases enormous amounts of energy. The core, which had been contracting, suddenly stops. The flood of energy pushes outward, and the core stabilizes once again. With the core now fusing helium into carbon, the star enters a new stable phase. It's still a giant, still red, but it has achieved a new balance. For a time, perhaps 100 million years for a star like the Sun, it will fuse helium in its core while continuing to burn hydrogen in a shell. It's living on borrowed time, fusing the ashes of hydrogen fusion into carbon and oxygen, creating elements that did not exist in the primordial universe. Think about that for a moment. Every carbon atom in your body was created inside a star. Not just any star, but a star in its red giant phase, fusing helium in its core. You are, quite literally, made of material that was forged in the hearts of dying suns. The phrase, "we are stardust," is not poetic metaphor, It's sober scientific fact. But even this new lease on life doesn't last forever. Eventually, the helium in the core runs out. Once again, the star is left with an inert core, now made of carbon and oxygen, surrounded by shells of burning helium and hydrogen. The core contracts again. The star expands further. It might shed its outer layers in great pulses, blowing shells of gas out into space. It's becoming unstable, the fusion shells flickering and varying in intensity. For stars like the Sun, this is as far as the cycle goes. The core never gets hot enough to fuse carbon. Why? Because the core's mass isn't great enough. In stars, more mass means more gravity, means more compression, means higher core temperatures. The Sun's core simply doesn't have the mass needed to squeeze down to the billion-degree temperatures required to fuse carbon. And so the Sun, 5 or 6 billion years from now, will find itself in a precarious situation. It will be a bloated red giant, perhaps twice as luminous as it is now, with a contracting carbon-oxygen core surrounded by unstable fusion shells. Its outer layers will be only loosely bound to the star, extended so far from the core that gravity's hold on them is tenuous. What happens next is beautiful and elegiac. The star begins to shed those outer layers, gently at first, then more rapidly. Stellar winds, streams of particles flowing away from the star, blow the outer layers out into space. Over thousands of years, the red giant sheds its outer envelope entirely, casting it off into the cosmos, like a butterfly emerging from a cocoon. Left behind is the hot, dense core, no longer fusing anything, no longer generating energy, and surrounding it, expanding slowly outward, is a shell of glowing gas illuminated by the radiation from the exposed core. This is a planetary nebula, though the name is misleading. It has nothing to do with planets. Early astronomers thought these objects looked like planets through their telescopes, and the name stuck. Planetary nebulae are among the most beautiful objects in the universe. They come in a stunning variety of shapes: spheres, rings, hourglasses, butterflies. Each one is the funeral shroud of a star like the Sun, cast off in the final stages of its life. The Ring Nebula, the Cat's Eye Nebula, the Helix Nebula. These are all planetary nebulae, the elegant final gestures of dying stars. And at the center of each planetary nebula, where the star once shone, there remains the core. Small, hot, dense, no longer generating new energy, but still radiating the heat accumulated over billions of years of fusion. This remnant core has a name. We call it a white dwarf. Let's drift closer to one of these white dwarfs and see what it is. This strange ember of a once bright star, this final resting state of the Sun and all stars like it. White dwarfs, the embers of stellar death. A white dwarf is not like other stars. It's not even really a star anymore, at least not in the traditional sense. It's not fusing anything in its core. It's not generating new energy. It's simply a dense sphere of carbon and oxygen, about the size of Earth, glowing white-hot from the leftover thermal energy of its long life. Let me say that again, because it's worth emphasizing. A white dwarf has about the same mass as the Sun, but compressed into a sphere about the size of Earth. Imagine taking the entire mass of the Sun, hundreds of thousands of times more massive than Earth, and crushing it down until it's Earth-sized. The resulting density is staggering. A teaspoon of white dwarf material would weigh as much as an elephant, or a car. Or, for the most dense white dwarfs, a small mountain. How is this possible? What prevents the white dwarf from collapsing further under its own immense gravity? The answer lies in quantum mechanics, in a principle called electron degeneracy pressure. In ordinary matter, electrons orbit around atomic nuclei, occupying specific energy levels. But in a white dwarf, the matter is so compressed that electrons are stripped from their atoms entirely. They become what's called a degenerate electron gas. These free electrons are subject to the Pauli exclusion principle, a quantum mechanical rule that states no two identical fermions, particles like electrons, can occupy the exact same quantum state. In a white dwarf, the electrons are packed so tightly that they're essentially forced into their lowest possible energy states. Any further compression would require electrons to occupy states that are already taken, which quantum mechanics forbids. The result is a pressure, not a thermal pressure from heat, but a quantum pressure from the electron's resistance to being squeezed any further. This electron degeneracy pressure is what holds up a white dwarf against gravity's crush. It's not fusion, not heat, but the fundamental quantum nature of matter itself that keeps the star from collapsing. It's a bit like trying to pack more people into an already full elevator. At some point, there simply isn't room for one more person. The people themselves, just by occupying space, create a pressure that resists further crowding. White dwarfs are held up by a similar principle, except instead of people in an elevator, it's electrons squeezed into the smallest possible spaces that quantum mechanics allows. When a white dwarf first forms, it's extraordinarily hot, perhaps 100,000 degrees at its surface. It glows white, or even bluish white, hence the name. But unlike a normal star, it has no internal source of energy. It's not fusing anything, it's just hot. And over time, very gradually, it will cool. This cooling process is remarkably slow. A white dwarf radiates heat into space, but it has no atmosphere to speak of, no convection to carry heat from the interior to the surface. Heat can only escape through the slow process of thermal conduction. As a result, white dwarfs can take tens of billions of years to cool down. The universe is only about 14 billion years old, so even the oldest white dwarfs are still reasonably warm. None have had time to cool completely. As a white dwarf cools, its color changes, from white to yellow to red to, eventually, a dull dark object that emits almost no light. This final state is called a black dwarf, though it's purely theoretical. Again, no white dwarf has had time to cool that much yet. When the universe is 100 trillion years old, when all the stars have long since burned out, the cosmos will be littered with black dwarfs, the cold remnants of dead stars, invisible in the darkness. But that's a long way off. For now, white dwarfs still shine, still glow, still light up small corners of space. Sirius B, the faint companion to Sirius, the brightest star in our night sky, is a white dwarf. 40 Eridani b is another, visible through a modest telescope. These stellar corpses drift through space, cooling slowly, glowing like embers in the cosmic night. One curious fact about white dwarfs: the more massive they are, the smaller they are. This seems counterintuitive, but it's a consequence of how gravity and electron degeneracy pressure interact. A more massive white dwarf has stronger gravity, which compresses it more, making it smaller. A less massive white dwarf has weaker gravity and is therefore larger. There's even a theoretical limit to how massive a white dwarf can be. This limit is called the Chandrasekhar limit, named after the Indian-American astrophysicist Subrahmanyan Chandrasekhar, who calculated it in the 1930s. The limit is about 1.4 times the mass of the Sun. If a white dwarf ever exceeds this mass, electron degeneracy pressure can no longer support it. The star will collapse. And what happens then is catastrophic, spectacular, and cosmically important. We'll come to that shortly. For now, though, consider the fate of our Sun. 5 or 6 billion years from now, after its red giant phase, after casting off its outer layers as a planetary nebula, the Sun will become a white dwarf. No longer burning, no longer shining with the fire of fusion, it will simply glow with leftover heat, slowly cooling over billions of years. Any planets that survive, perhaps the outer worlds like Jupiter and Saturn, will orbit a white dwarf sun, illuminated by its dim, cool light. Earth, if it hasn't been consumed, will be a charred, frozen world, airless and lifeless, orbiting what remains of its star. It's a sobering image, but also strangely peaceful. The sun won't die in violence, It will simply fade, gently, into the night. This is the fate of most stars. Stars like the Sun, and all smaller stars, will one day become white dwarfs. They'll cool and dim, and eventually fade from view, but they'll endure. They're stable. They won't collapse further. They'll exist, unchanging, for time spans that dwarf the current age of the universe. But not all stars follow this gentle path. More massive stars, those with more than about 8 times the Sun's mass, have a different destiny. They cannot end as white dwarfs. Their cores grow too massive, exceeding the Chandrasekhar limit. And when that happens, the story becomes far more dramatic. Let's turn our attention now to these massive stars and their spectacular deaths. Supernovae. When stars go out in glory. Massive stars live very different lives than the Sun. They burn hotter, brighter, faster, and they die in ways that are almost impossible to comprehend. In explosions so violent, so energetic, that a single star can briefly outshine an entire galaxy containing hundreds of billions of stars. Let's follow the life of a massive star, one with perhaps 20 times the Sun's mass. Like all stars, it begins on the main sequence, fusing hydrogen into helium, but it burns through its hydrogen fuel in just a few million years, a cosmic eye blink compared to the Sun's 10 billion year lifespan. When the hydrogen is exhausted, the core contracts and heats up, just as in a Sun-like star. A shell of hydrogen begins to burn around the core. But here's where massive stars diverge from their smaller cousins. The core of a massive star contracts more forcefully because there's more mass, more gravity. It heats up more, gets denser, reaches higher temperatures. And when it reaches 100 million degrees, helium fusion begins. Not in a sudden flash, but smoothly, controlled. The core fuses helium into carbon and oxygen, as the Sun will one day do. But then, when the helium runs out, something remarkable happens. The massive star doesn't stop. Its core is heavy enough, massive enough, that it can continue contracting, continue heating up. The temperature reaches 600 million degrees. At this temperature, carbon begins to fuse. Carbon nuclei combine to create neon and magnesium. The star has entered a new phase of life, one that smaller stars can never reach. From here, the process accelerates. When the carbon is exhausted, the core contracts further. Neon fuses, creating oxygen and magnesium. Then oxygen fuses, creating silicon and sulfur. Each stage happens faster than the last. Carbon burning might last for 10,000 years. Oxygen burning lasts for just 6 months. Silicon burning, the final stage, lasts about 1 day. During silicon burning, the core reaches temperatures of 3 billion degrees. Silicon nuclei fuse in complex chains, gradually building up heavier and heavier elements until finally they create iron. And here, the process stops. Iron cannot be fused to release energy. In fact, fusing iron requires energy rather than releasing it. For a star, iron is poison. It's the end of the line. You can think of the massive star at this point as having an onion-like structure. At the center is an iron core, about the size of Earth but with the mass of the Sun. Around it is a shell where silicon is fusing into iron. Around that, a shell where oxygen is fusing into silicon. Then shells of neon burning, carbon burning, helium burning, and finally hydrogen burning in the outermost layers. It's like a Russian nesting doll of fusion processes, each shell at a different temperature, burning a different element. But the iron core is growing. With every passing second, more silicon fuses into iron, adding to the core's mass. And iron, remember, cannot fuse to generate energy. There's no outward pressure from fusion to support the iron core. It's held up only by electron degeneracy pressure, the same quantum pressure that supports white dwarfs. And then, perhaps within hours, the iron core reaches the Chandrasekhar limit, about 1.4 solar masses. At this point, not even electron degeneracy pressure is enough. The gravity of the core overwhelms the quantum pressure. The core collapses. What happens next occurs so fast that it's difficult to grasp. The iron core, about the size of Earth, collapses in less than a second. In a fraction of a heartbeat, it shrinks from the size of a planet to a sphere perhaps 20 kilometers across. It's one of the fastest, most violent events in the universe. The core's collapse releases more gravitational energy in 1 second than the Sun will emit in its entire 10 billion year lifetime. During this collapse, something remarkable occurs. Electrons are forced to combine with protons, creating neutrons and releasing neutrinos. The core becomes a neutron star, a sphere of pure neutron matter, held up by neutron degeneracy pressure. But we'll come back to neutron stars in a moment. First, let's see what happens to the rest of the star. As the core collapses, the outer layers of the star, which had been held up by the pressure from below, suddenly find that support gone. They begin to fall inward. Trillions of tons of matter, the entire mass of the star outside the core, plummets down at speeds approaching 1/10 the speed of light. But this infalling matter doesn't reach the core. When the core reaches neutron star density, it abruptly stops collapsing. It becomes incredibly stiff, effectively incompressible. The infalling matter slams into the surface of the neutron star and bounces. A shockwave forms, a wall of compressed, superheated matter moving outward through the star at thousands of kilometers per second. This shockwave is amplified by neutrinos streaming out from the newly formed neutron star. 99% of the energy released in the core collapse is carried away by neutrinos, ghostly particles that barely interact with matter. But in the extreme densities near the core, even neutrinos are absorbed by the infalling material. They heat it up, give energy to the shockwave, and help it blast through the star's outer layers. The shockwave reaches the surface of the star in a matter of hours. When it does, it blows the star apart in an explosion of unimaginable violence. This is a core collapse supernova. The brightness can rival that of an entire galaxy. For a few weeks, a single dying star can be the most luminous object in its region of the universe. Let's pause and consider what we're talking about. A star, an object that has shone steadily for millions of years, suddenly, in the space of a few hours, tears itself apart with such force that it can be seen from the other side of the universe. The energy released is equivalent to what the Sun will emit over its entire lifetime, but compressed into a brief, brilliant flash. Supernovae are rare. In our galaxy, they occur perhaps once or twice per century. The last one visible to the naked eye was in 1604, observed by Johannes Kepler. Before that, Tycho Brahe saw one in 1572. In 1054, Chinese and Arabic astronomers recorded a supernova so bright it was visible during the day. Its remnant, the Crab Nebula, is still expanding outward today, a beautiful, complex tangle of gas and magnetic fields, powered by the spinning neutron star at its heart. We've been lucky, or perhaps unlucky, depending on your perspective, not to witness a nearby supernova in modern times. But when Betelgeuse finally explodes, and it will someday, though we don't know exactly when, it will be spectacular. For a few weeks, Orion will have two bright stars where there was once one. Betelgeuse will glow brilliantly, perhaps as bright as the full moon, visible even in broad daylight, and then it will fade, leaving behind a remnant, a nebula, and possibly a neutron star or black hole. But supernovae are not just spectacular light shows. They are crucially important to the chemical evolution of the universe. Remember all those layers of the star, the shells burning carbon, oxygen, silicon. In the violence of the supernova explosion, all of that material is blasted out into space. Along with it comes newly synthesized elements created in the explosion itself. In the extreme temperatures and densities of a supernova, elements heavier than iron can be created. Gold, platinum, uranium, elements that cannot form in normal stellar fusion, are forged in the supernova's crucible. When you wear a gold ring, You're wearing an element that was created in a supernova explosion billions of years ago, perhaps before the sun even formed. Supernovae seed the galaxy with heavy elements. The cloud of gas and dust from which new stars form is enriched by supernova ejecta. Each generation of stars is born with more heavy elements than the last. The first stars, formed shortly after the Big Bang, contained only hydrogen and helium. But the Sun, a relative latecomer born 5 billion years ago, contains carbon, oxygen, iron, and traces of nearly every element in the periodic table. Those elements came from supernovae, from the deaths of earlier generations of stars. This is why we say we are made of stardust, the calcium in your bones, the iron in your blood, the carbon in your DNA. All of it was forged in stars and scattered by supernovae. You are, quite literally, assembled from the remnants of stellar explosions. Every atom in your body, except for hydrogen, was created either in the quiet fusion of a star's core or in the violent chaos of a supernova. It's a humbling thought, and a beautiful one. We are not separate from the cosmos. We are part of it. We are the universe examining itself. Matter become conscious, stardust contemplating its origins. The iron in your bloodstream is the same iron forged in a massive star's core 5 billion years ago. That atom witnessed the star's explosion, drifted through interstellar space for millions of years, was incorporated into the cloud that formed the sun, ended up in a rocky planet, and eventually, through the slow work of evolution, became part of you. So when you look up at the stars, remember that you are looking at family. Distant cousins perhaps, but family nonetheless. The same processes that built them built you. The same elements that shine in their light flow through your veins. You and the stars are made of the same stuff, shaped by the same laws, connected by the deep history of the cosmos. But we're not done yet. What happens to the core of the star after the supernova? We briefly mentioned neutron stars. Let's explore them now. These strange, exotic objects, perhaps the most extreme examples of matter that can exist in the universe. But first, let's take a detour through another fascinating aspect of stellar life: binary stars and the complex dance of gravity that occurs when stars exist in pairs or groups. Binary stars, the dance of cosmic companions. So far, we've talked about stars as if they exist in isolation, each one shining alone in the darkness. But that's not the full picture. Most stars, perhaps 2/3 or more, exist in binary or multiple star systems. They have companions, other stars gravitationally bound to them, orbiting a common center of mass. And when stars have companions, their lives can become far more complex and dramatic. A binary star system is simply two stars orbiting each other. They're bound by gravity, trapped in an eternal dance, circling their common center of mass. This center of mass is called the barycenter, and it's the point around which both stars orbit. If the stars are equal in mass, the barycenter is exactly halfway between them. If one star is more massive, the barycenter is closer to it. In extreme cases, say a massive star with a much smaller companion, the barycenter might be inside the more massive star itself. Binary stars come in many varieties. Some are visual binaries, close enough and bright enough that we can see them as separate stars through a telescope. Albireo, in the constellation Cygnus, is a beautiful visual binary. One star golden yellow, the other blue. They're separated by enough distance that you can easily see both through even a small telescope. They orbit each other once every 75,000 years or so, a glacially slow dance, but a dance nonetheless. Other binaries are too close together to separate visually, but we know they're binaries because their spectra show periodic Doppler shifts. As the stars orbit, sometimes one moves toward us while the other moves away. The Doppler effect shifts their spectral lines, one toward blue, one toward red. By watching these shifts over time, we can determine the stars' orbital periods and even calculate their masses. And then there are eclipsing binaries, where the orbital plane happens to be edge-on to Earth. As the stars orbit, they periodically pass in front of each other from our perspective, causing the combined brightness to dip. Algol, in Perseus, is a famous eclipsing binary. Ancient astronomers called it the demon star because of its strange behavior. Every 2.87 days, it dims noticeably for several hours as the dimmer companion passes in front of the brighter star. When binary stars are far apart, they evolve independently, each following its own path from main sequence to red giant to white dwarf or supernova. But when they're close together, close enough that their outer atmospheres can interact, things get interesting. And by interesting, I mean occasionally spectacular, sometimes catastrophic, always fascinating. Each star in a binary has what's called a Roche lobe, a teardrop-shaped region around it where its gravity dominates. Material within a star's Roche lobe is bound to that star. But if a star expands beyond its Roche lobe, which can happen when it becomes a red giant, some of its material can spill over to the companion. This is called Roche lobe overflow, and it's responsible for some of the most exotic phenomena in astronomy. Imagine a binary system where one star is a bit more massive than the other. The more massive star evolves faster, becoming a red giant, while its companion is still on the main sequence. As the giant swells, it reaches and exceeds its Roche lobe. Gas from the giant's outer layers begins to flow toward the companion, spiraling inward in a disk called an accretion disk. Accretion disks are incredibly hot and luminous. As gas spirals inward, friction heats it up. The inner parts of the disk can reach temperatures of millions of degrees, hot enough to emit X-rays. So a star that's peacefully stealing gas from its companion can become an X-ray source, visible to X-ray telescopes, but possibly dim or even invisible in normal light. This mass transfer can dramatically affect the evolution of both stars. The star losing mass might be stripped down to its core, becoming a helium star, or even exposing layers that were never meant to see the light of day. The star gaining mass becomes more massive, hotter, and burns faster. It's no longer following the single-star evolutionary path we described earlier. It's on a new track, one that can lead to outcomes impossible for isolated stars. And it gets stranger. Imagine now that the first star, after losing mass to its companion, finishes its evolution and becomes a white dwarf. The companion, now more massive than before, eventually evolves into a red giant itself. And when it does, the same process happens in reverse. The red giant expands, exceeds its Roche lobe, and begins transferring mass back, but now it's transferring onto a white dwarf. A white dwarf accreting material from a companion is called a cataclysmic variable, and it's aptly named. The gas doesn't fall gently onto the white dwarf. It spirals inward in an accretion disk, heating up to extreme temperatures. When enough material accumulates on the white dwarf's surface, it can ignite in a thermonuclear explosion. This is a nova, not to be confused with a supernova, though the name similarity has caused endless confusion. A nova is a surface explosion on a white dwarf. It doesn't destroy the star, it just blows off the accreted material in a brief, brilliant flash. The white dwarf remains intact and, after the nova fades, continues accreting material from its companion. Eventually, it accumulates enough material for another nova. Some systems undergo nova explosions every few years or decades, recurrent novae, caught in a cycle of accretion and explosion. But here's where it gets truly dramatic. Remember the Chandrasekhar limit, the maximum mass a white dwarf can have. If a white dwarf keeps accreting material from its companion, it can approach and eventually exceed this limit. And when it does, the white dwarf can't support itself anymore. It collapses. The entire white dwarf, not just the accreted surface layer, undergoes runaway fusion. Carbon and oxygen fuse explosively, releasing enormous energy. The white dwarf tears itself apart in a Type Ia supernova. Type Ia supernovae are crucial to astronomy because they're remarkably consistent in brightness. Unlike core collapse supernovae, which vary widely depending on the progenitor star, Type Ia supernovae all involve white dwarfs, reaching the Chandrasekhar limit. They all explode with similar energy. This makes them excellent standard candles for measuring cosmic distances. In fact, type Ia supernovae are what revealed that the universe's expansion is accelerating, a discovery that led to the idea of dark energy. But binary stars can create even stranger objects. Consider a binary where both stars are massive enough to become neutron stars. They'll orbit each other closely, two incredibly dense objects spinning around a common center. But here's the thing. Orbiting objects emit gravitational waves, ripples in space-time predicted by Einstein's general relativity. These waves carry away energy, causing the orbit to slowly decay. The neutron stars spiral inward. Eventually, after perhaps millions or billions of years, the neutron stars collide. The collision is incredibly violent. Two objects, each more massive than the Sun, but only 20 kilometers across, smashing together at a significant fraction of the speed of light. The result is a kilonova, an explosion that creates heavy elements through rapid neutron capture and emits gravitational waves strong enough to be detected by instruments on Earth. In 2017, astronomers detected gravitational waves from such a collision. It was the first time gravitational waves and electromagnetic light from the same event were observed simultaneously. Telescopes around the world turned toward the source and watched as the kilonova brightened, glowed blue, then red, and faded over weeks. Analysis suggested the collision produced several Earth masses worth of gold and platinum. Every gold atom you've ever seen might have been forged in such a merger billions of years ago. Binary stars can also create something even more exotic, a system where one component is a black hole. If one star in a binary is massive enough, it can end its life as a black hole rather than a neutron star. The companion might be a normal star, still on the main sequence. As the companion evolves and expands, it begins transferring mass to the black hole. The infalling material forms an accretion disk around the black hole, glowing brilliantly in X-rays as it spirals inward toward the event horizon. Cygnus X1, one of the strongest X-ray sources in the sky, is likely such a system. A black hole with about 15 times the Sun's mass is accreting gas from a blue supergiant companion. The system is so close that the companion completes an orbit every 5.5 days. It's slowly being consumed, its gas stolen away by the black hole's immense gravity, heating to millions of degrees as it spirals inward. There are even triple and quadruple star systems, where 3 or 4 stars orbit in complex arrangements. Polaris, the North Star, is actually a triple system. Alpha Centauri, our closest stellar neighbor, is a triple. 2 sun-like stars in close orbit, plus Proxima Centauri, a red dwarf orbiting far out. These multiple systems can be remarkably stable. Their orbits, choreographed by gravity into dances that last for billions of years. All of this complexity arises from one simple fact. Stars don't always form alone. When a molecular cloud collapses, it often fragments, forming multiple stars. These stars are born close together, and if they're close enough, gravity binds them permanently. They become binary, or multiple systems, their fates forever intertwined, their evolution shaped not just by their own properties, but by the presence of their companions. And perhaps there's something poetic about that. Stars, for all their vast power and cosmic importance, don't exist in isolation. They're social objects, bound to companions, their lives shaped by relationships. A star in a binary will live a different life than a solitary star. It might gain mass from its companion, or lose mass to it. It might trigger its companion's death, or be destroyed by its companion's violence. In the end, its story is not just its own. It's a shared story, written in gravity and light, played out over billions of years. So when you look up at the night sky, remember that many of those points of light are not single stars, but pairs or groups, bound together by gravity, orbiting each other in the darkness. Some are tearing each other apart. Others are feeding each other gas. Some are spiraling together, destined to collide billions of years from now. Each system is unique, each is complex, and each adds another layer to the rich tapestry of the cosmos. Now, having explored the complex interactions of binary stars, let's return to the aftermath of supernovae and explore those incredibly strange objects left behind, neutron stars. Objects so dense, so extreme, that they challenge our understanding of what matter can be. Neutron stars, hearts of collapsed giants. After a supernova, if the core is between about 1.4 and 3 solar masses, what remains is a neutron star. If that sounds ordinary, I assure you it is anything but. Neutron stars are among the strangest, most extreme objects in the universe. They're only about 20 kilometers across, small enough to fit within a city, but they contain more mass than the Sun. The density is almost incomprehensible. Let's try to grasp this density. A neutron star's matter is so tightly packed that a sugar cube-sized chunk would weigh about 100 million tons on Earth. That's roughly the mass of all of humanity compressed into the volume of a die. If you could somehow scoop up a teaspoon of neutron star material and bring it to Earth, it would weigh about 1 billion tons, more than all the cars on the planet combined. At these densities, atoms don't exist, not in any normal sense. The protons and electrons that make up atoms are forced to combine, creating neutrons. The entire star becomes, essentially, a single giant atomic nucleus made of neutrons packed together so tightly, they're almost touching. It's matter in a state that can't exist anywhere on Earth. Matter compressed to the very edge of what physics allows. What holds up a neutron star? Just as electron degeneracy pressure supports white dwarfs, neutron degeneracy pressure supports neutron stars. Neutrons, like electrons, are fermions subject to the Pauli exclusion principle. They resist being forced into the same quantum states. This resistance creates a pressure strong enough, barely, to hold up a neutron star against its own crushing gravity. Neutron stars have several remarkable properties beyond their density. First, they spin, and they spin fast, really, really fast. When the core of a massive star collapses to form a neutron star, conservation of angular momentum ensures that any rotation in the original core is amplified. It's like an ice skater pulling in their arms to spin faster, except far more extreme. A star that was slowly rotating once per month might collapse into a neutron star that rotates several times per second. The fastest known neutron star rotates 716 times per second. Let me say that again, 716 rotations per second. That's an object with more mass than the Sun, spinning so fast that its equator is moving at a significant fraction of the speed of light. If you could stand on such a neutron star's surface, which you can't, for a variety of lethal reasons, you'd complete a full rotation around the star's axis in less than a millisecond. Neutron stars also have incredibly strong magnetic fields. The Sun's magnetic field, which is strong enough to create sunspots and solar flares, is about 1 Gauss at its surface. A typical neutron star might have a surface magnetic field of 1 trillion Gauss. The strongest magnetic fields known, on objects called magnetars, can reach 1 quadrillion Gauss or more. These are the strongest magnetic fields in the universe. Such a magnetic field would be instantly lethal at close range. It would disrupt the molecular bonds in your body, interfere with your nervous system, make your atoms themselves behave strangely. You wouldn't need to get very close. Within a few thousand kilometers, the magnetic field would kill you. And that's before considering the intense gravity, the radiation, and the X-rays the neutron star emits. Some neutron stars are observable as pulsars. A pulsar is simply a neutron star whose magnetic axis is tilted relative to its rotation axis. As the star spins, the magnetic field rotates with it. Charged particles near the star's surface are accelerated along the magnetic field lines, creating intense beams of radiation that shoot out from the magnetic poles. If one of these beams happens to point toward Earth as the neutron star rotates, we see a pulse of radiation, like a cosmic lighthouse. Each time the beam sweeps past, we detect a brief flash. Some pulsars pulse hundreds of times per second, their signals so regular that they rival the best atomic clocks on Earth. When pulsars were first discovered in 1967, their signals were so precise and regular that astronomers briefly wondered if they might be artificial, signals from an alien civilization. They were dubbed LGM-1 for Little Green Men. But no, just neutron stars, spinning in the darkness, their geometry and rotation conspiring to send pulses of light sweeping across the cosmos. Neutron stars are also interesting because of their effect on space-time. Their gravity is so intense that they significantly warp the fabric of space and time around them. According to Einstein's general relativity, mass and energy curve space-time, and this curvature is what we experience as gravity. Near a neutron star, space-time is curved so strongly that time itself runs slower. If you could orbit close to a neutron star and then return to Earth, you'd find that less time had passed for you than for people who stayed behind. It's not a metaphor or an approximation. Time actually flows at different rates depending on how deep you are in a gravitational field. Near a neutron star, this effect is substantial. An hour near the surface might correspond to several hours for a distant observer. Neutron stars can also collide. When two neutron stars in a binary system spiral together and merge, the resulting explosion is called a kilonova. It's not as bright as a supernova, but it's still spectacularly energetic. And it's incredibly important because kilonova explosions are where many of the heaviest elements are created. Remember how supernovae create elements heavier than iron? Well, neutron star mergers are even better at it. In the extreme conditions of a kilonova, temperatures of billions of degrees, densities approaching those inside atomic nuclei, rapid neutron capture can occur. Neutrons are added to atomic nuclei so quickly that very heavy, neutron-rich isotopes form. These then decay into stable heavy elements like gold, platinum, and uranium. In 2017, astronomers detected gravitational waves from a neutron star merger, along with light across the electromagnetic spectrum. It was the first time such an event had been observed in multiple ways simultaneously. The analysis suggested that the collision produced several Earth masses of gold and platinum. Every gold atom in existence may have been forged in such a collision, created in the violent merger of two dead stars. So neutron stars are not just interesting for their own sake. They're crucial to understanding how heavy elements are distributed through the universe. They're cosmic forges, alchemical laboratories, where the heaviest atoms are created and then scattered through space, eventually finding their way into planets, asteroids, and perhaps one day, into the heart of a circuit board or the ring on someone's finger. But neutron stars have a limit too. Just as there's a maximum mass for a white dwarf, there's a maximum mass for a neutron star. We're not exactly sure what that mass is, somewhere between 2 and 3 times the mass of the Sun, but we know it exists. Above this mass, even neutron degeneracy pressure cannot prevent collapse. And when a neutron star exceeds this limit, it collapses into the most extreme object in the universe, a black hole. Black holes deserve their own extended discussion, but in the context of stellar evolution, they represent the final fate of the most massive stars. When a star much more massive than the Sun explodes as a supernova, its core may be so massive that it doesn't stop at the neutron star stage. It just keeps collapsing, past neutron star density, past any known form of matter, until it becomes a singularity, a point of infinite density hidden behind an event horizon, a boundary in space-time beyond which nothing, not even light, can escape. But black holes, fascinating as they are, take us beyond the scope of stellar life and death. They're more than just dead stars. They're something else entirely, objects so strange and extreme that they challenge our understanding of physics itself. For now, let's step back and look at the broader picture. We've followed stars from birth to death, From nebulae to main sequence to red giants to white dwarfs, or from nebulae to main sequence to supernovae, to neutron stars or black holes. It's time to ask, what does all this mean? What can we learn from the life cycles of stars? We are stardust, the chemical evolution of the universe. Throughout this journey, we've mentioned several times that we are made of stardust. It's a phrase that's become almost a cliché, repeated so often it might have lost its impact. But let's take a moment now to really understand what it means. Let's trace the journey of atoms, from the hearts of dying stars to your body. Lying here listening to these words, it's a story of chemistry, of violence, of patience, and of the most extraordinary coincidences. In the beginning, and by beginning, I mean about 380,000 years after the Big Bang, the universe contained only 3 elements: hydrogen, helium, and traces of lithium. That's it. No carbon, no oxygen, no iron. None of the elements that make up rocks, water, air, or life. The universe was chemically simple, almost boring. Just the lightest elements, created in the Big Bang itself, drifting through space as the universe expanded and cooled. Then, about 100 to 200 million years after the Big Bang, the first stars formed. These population 3 stars were massive, perhaps hundreds of times the mass of the Sun, formed from pure hydrogen and helium. They were short-lived, burning hot and fast, living for just a few million years. And when they died, they created the first heavy elements. In their cores, through fusion, they created carbon, oxygen, neon, magnesium, silicon, elements that had never existed before. And when they exploded as supernovae, they created even heavier elements: iron, nickel, copper, zinc, and beyond. These elements were scattered through space, mixing with the primordial hydrogen and helium, creating the first chemically enriched gas clouds. The next generation of stars formed from this enriched gas. They contained not just hydrogen and helium, but traces of heavier elements, perhaps 1 atom in 100,000. This doesn't sound like much, but it was revolutionary. For the first time, stars contained carbon, oxygen, silicon. For the first time, when these stars formed planetary disks, those disks could contain rocky material. Planets could form, not just gas giants like Jupiter, but rocky worlds like Earth. This process continued, generation after generation. Stars formed, lived, died, and scattered their elements. Each generation was slightly richer in heavy elements than the last. Slowly, over billions of years, the universe became chemically complex. The hydrogen and helium that made up 98% of the early universe gradually mixed with heavier and heavier elements, until by the time the Sun formed, about 2% of the galaxy's mass was in elements heavier than helium. This 2% might not sound significant, but it made all the difference. Earth is made almost entirely from that 2%. The oxygen you breathe, the carbon in your cells, the calcium in your bones, the iron in your blood. All of it comes from that small fraction of heavy elements created in stars over billions of years and gradually accumulated in the solar nebula from which the Sun and planets formed. Let's trace the journey of a specific atom, say, a carbon atom in your body. That atom was created inside a red giant star, perhaps 8 billion years ago. The star was fusing helium in its core through the triple alpha process, creating carbon nuclei. Your carbon atom was one of these newly created nuclei, deep in the star's core, surrounded by the intense heat and pressure of ongoing fusion. When that star evolved into a planetary nebula, your carbon atom was part of the material ejected into space. It drifted for millions of years, part of an expanding shell of gas, glowing in the light of the white dwarf that the star had become. Eventually, the gas cooled and dispersed, mixing with the interstellar medium, the thin gas that fills the space between stars. For billions of years, your carbon atom drifted through space, sometimes part of a diffuse cloud, sometimes floating alone through the near vacuum between the stars. It might have been part of several clouds that never collapsed, that simply dispersed again. It waited, patient and unconscious, for the right conditions. About 4.5 billion years ago, your carbon atom became part of a cloud that was collapsing to form a new star, our Sun. As the cloud collapsed, most of the material fell into the growing star, but some remained in a disk around it. Your carbon atom was in that disk, orbiting the young Sun, colliding with other atoms and dust grains, gradually accumulating into larger and larger clumps. Eventually, after millions of years of collisions and accretion, your carbon atom became part of Earth. Perhaps it was incorporated into a rock. Perhaps it cycled through Earth's interior, brought to the surface by volcanic activity, weathered into soil. Perhaps it was absorbed by an ancient organism billions of years ago, became part of a cell, and then was released again when that organism died. Over billions of years, your carbon atom cycled through Earth's carbon cycle. It might have been atmospheric CO2. It might have dissolved in the ocean. It might have been part of a tree, a dinosaur, a trilobite, a bacterium. Each time, it was used by life, released, reused again. It witnessed the entire history of Earth, though of course, it had no consciousness, no memory. It was just an atom, subject to the laws of chemistry and physics, moved around by random chance and the processes of geology and biology. And then, recently, perhaps just years or months ago, you ate a plant or an animal that contained that carbon atom. Your digestive system broke down the food, and that atom was absorbed into your bloodstream. It became part of your body. Perhaps it's in a cell in your brain right now. Perhaps it's part of a bone, a muscle, a hair. At this moment, that carbon atom is you. Part of your physical structure, part of what makes you material rather than merely an idea. And eventually, days or months or years from now, that atom will be released. You'll breathe it out as CO2, or excrete it, or it will be released when your body eventually returns to the Earth. And then it will continue its journey, cycling through the biosphere and geosphere, perhaps eventually being incorporated into another person, another organism, another structure. The atom's journey continues, endless, until perhaps billions of years from now, when the Sun becomes a red giant and Earth is destroyed. The atom will be released back into space to begin the cycle again. This is true for every atom in your body, heavier than hydrogen. The oxygen atoms in the water in your cells were created in the cores of massive stars and scattered by supernovae. The calcium atoms in your bones were created in dying stars. The iron atoms in your hemoglobin were created in a star's core just before it exploded. Even the gold in any jewelry you might wear was created in a neutron star merger billions of years ago. You are not just metaphorically made of stardust. You are literally assembled from atoms that were created in stellar cores, forged in the hearts of dying stars, scattered through space by supernovae and stellar winds, accumulated in the solar nebula, incorporated into Earth, and eventually arranged into the complex structure that is you. Your atoms are billions of years old. They've traveled light years through space. They've witnessed the formation of solar systems and the evolution of galaxies. And here's the remarkable thing. The same is true for everything around you. The oxygen you're breathing was created in stars. The water you drink contains oxygen and hydrogen from the Big Bang and stellar processes. The Earth itself is made from stellar ash, the accumulated debris of countless dead stars. Everything you've ever touched, tasted, or seen is made from elements created in stars. This connects you not just to the stars, but to everyone and everything else. The carbon in your body, and the carbon in a tree, and the carbon in the Earth's crust all came from the same source, dying stars. You and the tree are literally made of the same stuff, arranged in different patterns. You and another person are assembled from atoms that were created in the same stellar processes, scattered by the same supernovae, drifting through the same regions of space before being incorporated into Earth. And this chemical evolution continues. Right now, stars are fusing lighter elements into heavier ones. Supernovae are scattering newly created elements through space. neutron stars are merging, creating the heaviest elements. The universe is slowly but steadily becoming more chemically complex, more metal-rich, more capable of forming rocky planets and sustaining complex chemistry. Billions of years from now, when the sun dies, Earth's atoms will be scattered back into space. Some of them might eventually become part of a new star system. The carbon, oxygen, and iron that are currently part of Earth might one day be part of a new rocky planet orbiting a new star. And if life arises on that planet, those atoms might become part of new organisms, continuing the cycle. In this sense, atoms are immortal. They can't be created or destroyed by normal chemical or physical processes. They can only be rearranged. The atoms that make up your body have existed for billions of years and will continue to exist for billions more. They've been part of stars, planets, oceans, organisms, and they'll continue being rearranged, incorporated into new structures, telling new stories for as long as the universe exists. This is the legacy of stars. They don't just light up the night sky. They create the elements. They make complexity possible. They seed the universe with the ingredients necessary for planets, chemistry, and life. Without stars, the universe would be forever simple, just hydrogen and helium, never forming anything more interesting than diffuse clouds of gas. But because stars exist, because they fuse elements and scatter them through space, the universe can be complex, diverse, beautiful. So yes, you are made of stardust, not as a poetic metaphor, but as a literal scientific fact. Your atoms were forged in stellar cores billions of years ago. They've traveled across the galaxy. They've witnessed cosmic history. And now, for a brief time, they're arranged in the form of you, conscious, aware, capable of understanding their own origins. It's a remarkable thing, perhaps the most remarkable thing in the universe, that matter can become aware of itself, can trace its own history, can understand where it came from and where it might be going. Let's carry this understanding forward now as we consider the deeper meaning of stars and what they tell us about our place in the cosmos. The meaning of stars, a cosmic perspective. So we've journeyed through the life and death of stars. We've watched nebulae collapse, protostars ignite, main sequence stars shine steadily for billions of years. We've seen red giants swell and glow, white dwarfs cool slowly into darkness. We've witnessed supernovae tear stars apart and neutron stars spin impossibly fast. It's been a long journey through space and time, measured in billions of years and vast cosmic distances. But what does it all mean? Why should we care about the life cycle of stars? These events occur over timescales so long and distances so vast that they feel almost abstract, disconnected from our daily lives. And yet, in a very real sense, the life and death of stars is the most important story there is. Because without stars, we wouldn't be here. Let's start with the most fundamental fact. Stars create the elements. In the first moments after the Big Bang, the universe contained only hydrogen and helium, with traces of lithium. That's it. 3 elements out of the 100 or so that exist naturally. Everything else, carbon, nitrogen, oxygen, iron, gold, uranium, was created inside stars or in stellar explosions. The carbon in your cells, the oxygen you breathe, the nitrogen in your DNA, the calcium in your bones, the iron in your blood, all of it was forged in stellar cores or supernova explosions. You are, quite literally, made from recycled star material, not metaphorically, not poetically. Actually, every atom in your body, heavier than hydrogen, was created inside a star. This is what Carl Sagan meant when he said, "We are made of star stuff." And this is what astrophysicists mean when they say we are stardust. It's not romantic language, it's sober scientific fact. The universe's first generation of stars contained no heavy elements at all. They were pure hydrogen and helium. When they died, they scattered the first heavy elements into space. Subsequent generations of stars formed from clouds enriched by these heavy elements, lived, died, and scattered even more elements. After billions of years of this cycle, enough heavy elements accumulated that rocky planets could form. Life could arise. And eventually, consciousness emerged. beings capable of looking back at the stars and understanding their own cosmic origins. So stars are not just distant lights in the sky. They're factories. They're the only places in the universe where the elements necessary for complexity can be created. Without stars, the universe would be forever simple, just hydrogen and helium, never coalescing into planets, never forming mountains or oceans, never giving rise to chemistry complex enough for life. But there's more. Stars are also clocks. Because they evolve in predictable ways, we can use them to measure cosmic time. When we look at a cluster of stars, we can determine its age by seeing which stars have evolved off the main sequence. Young clusters contain massive, bright blue stars that haven't had time to die yet. Old clusters contain only long-lived red dwarfs, because all the more massive stars have already burned out. Stars are also distance markers. We can use certain types of stars, Cepheid variables, RR Lyrae stars, and supernovae of a particular type, as standard candles to measure distances across the universe. By comparing how bright a star appears to how bright it actually is, we can calculate how far away it must be. This technique has allowed us to map the structure of our galaxy, measure the distances to other galaxies, and ultimately discover that the universe is expanding. Stars tell us about the evolution of galaxies. By studying the mix of elements in stars of different ages, we can reconstruct the chemical history of the galaxy. We can see how, over billions of years, the galaxy has been enriched with heavy elements. The oldest stars are metal-poor, containing almost no elements heavier than helium. Younger stars like the Sun are relatively metal-rich, having formed from gas that had been enriched by billions of years of stellar deaths. And stars connect us to the past and future in a way that's almost vertiginous. When you look at a star, you're seeing it as it was when its light left it, which might have been years, decades, or even thousands of years ago. The light from Alpha Centauri, our closest stellar neighbor, takes about 4 years to reach us. We see it as it was 4 years ago. Betelgeuse is about 650 light-years away. When we look at it, we're seeing light that left that star around the time of the Renaissance. In a sense, looking at the night sky is like looking into the past. The farther away a star is, the further back in time we're seeing. And if Betelgeuse has already exploded, which is possible, though we don't know, we won't find out until the light from that explosion reaches us. It might happen tomorrow, or it might have already happened centuries ago, and we just don't know it yet, because the light is still traveling toward us through the vastness of space. There's something profoundly moving about this. The stars are not just distant objects. They're our origins, our teachers, our guides to understanding the universe. They're also, in a sense, us. We are the universe looking back at itself. We are matter that has become conscious, aware, capable of wonder. And we use that consciousness to study stars, to understand how they work, to piece together the story of where we came from and where we might be going. Carl Sagan also once said that we are a way for the cosmos to know itself. And when you think about it, that's exactly what we are. The atoms in your brain were forged in stars billions of years ago. Those atoms have arranged themselves into a structure capable of thought, capable of understanding, capable of looking up at the night sky and recognizing its own origins. In you, the universe has become aware of itself. In every astronomer peering through a telescope, in every child gazing up at the stars in wonder, the cosmos is examining its own nature. This is not religious or spiritual language, though it might resonate with those perspectives. It's simply a description of what is. You are made of star material. Your atoms were created in stellar cores and dispersed by supernovae. Those atoms drifted through space, were incorporated into a cloud that collapsed to form the sun and planets, eventually became part of Earth, and through the slow work of evolution and time, arranged themselves into you, into consciousness, into wonder. So when you look up at the stars, remember that you are not separate from them. You are part of the same story, woven from the same threads, governed by the same laws. The stars are your ancestors. The elements they created flow through your veins. The light they emit has traveled across space and time to reach your eyes. You are connected to the cosmos in the most intimate, fundamental way possible. And in the far future, long after you're gone, the cycle will continue. The sun will expand into a red giant, perhaps engulfing Earth. It will shed its outer layers, creating a planetary nebula. At the center will be a white dwarf, slowly cooling over billions of years. And the elements scattered by the planetary nebula, including atoms that once were part of Earth, part of its oceans and mountains and forests, part of all the life that ever lived here, will drift through space, eventually becoming part of a new nebula, a new generation of stars and planets. Perhaps, billions of years from now, some of those atoms will become part of a new world. Perhaps life will arise there too. Perhaps consciousness will emerge once again, and beings on that distant future world will look up at their sky, see the stars shining, and wonder about their origins. And in a sense, those beings will be our descendants, made from the same atoms, continuing the same story, connected across vast gulfs of time and space by the simple fact that we're all made of stardust. That's the meaning of stars, if there is one. They're not just objects in the sky. They're the engines of complexity, the creators of elements, the ancestors of planets and life. They connect us to the cosmos and to the deep history of the universe. They remind us that we're part of something much larger than ourselves, something ancient and ongoing, something beautiful and profound. And perhaps, in understanding stars, we understand ourselves a little better too. We see that we're not separate from nature, but woven into its very fabric. We recognize that the universe is not a cold, hostile place, but the very source of our existence. We realize that every breath you take, every thought you think, every moment of joy and sorrow and wonder is made possible by stars that lived and died billions of years ago. So yes, stars matter, not just for astronomy or physics or science, but for understanding who we are, where we came from, and how we fit into the vast, beautiful tapestry of existence. Let's carry that understanding forward now as we bring this journey to a gentle close. Final reflections. The quiet majesty of stars. As we drift toward the end of our journey through the life and death of stars, let's take a moment to reflect on everything we've explored. We began in the quiet places between stars, in nebulae drifting through space. We watched as gravity gathered gas and dust, compressed it, heated it, until fusion ignited and a new star was born. We saw stars settle into billions of years of steady shining, fusing hydrogen into helium, maintaining that delicate balance between gravity and pressure. We watched as stars aged, as they exhausted their hydrogen fuel and swelled into red giants. We saw them fuse helium into carbon, perhaps even carbon into heavier elements if they were massive enough. We witnessed the gentle death of sun-like stars, shedding their outer layers to form planetary nebulae, leaving behind cooling white dwarfs that will glow for trillions of years. We explored the violent deaths of massive stars, supernovae that briefly outshine galaxies, scattering heavy elements through space, leaving behind neutron stars spinning impossibly fast, or black holes from which nothing can escape. We considered how these stellar deaths seed the galaxy with the elements necessary for planets, for chemistry, for life, and we contemplated what it all means. How every atom in our bodies was created in stars. How we are, in the most literal sense, stardust. The universe become conscious, looking back at itself, understanding its own nature. It's been a long journey, spanning billions of years and unimaginable distances. And yet, in another sense, we've barely scratched the surface. There's still so much we don't know about stars. We're not entirely sure how the very first stars formed, shortly after the Big Bang. We don't know exactly how supernovae explode, The physics is so complex that even our best computer simulations struggle to capture it. We're still discovering new types of stellar objects, new exotic behaviors, new mysteries that challenge our understanding. But that's part of what makes astronomy so fascinating. There's always more to learn, always new questions to ask. The universe is not a puzzle that can be solved once and for all. It's an endless source of wonder, constantly revealing new layers of complexity and beauty. Each answer we find leads to new questions. Each mystery we solve uncovers deeper mysteries. And perhaps that's fitting. Perhaps the universe isn't meant to be fully understood. Perhaps the joy is in the exploration, in the questioning, in the sense of awe that comes from contemplating something so vast and ancient and beautiful. The stars have been shining for billions of years. They'll continue shining long after we're gone. And in that, there's something both humbling and comforting. So, when you step outside on a clear night and look up at the stars, remember what you're seeing. You're seeing the past, light that left those stars years or centuries ago. You're seeing your origins. The very matter that makes up your body was forged in stellar cores. You're seeing the future. Those stars are still evolving, still changing, heading toward their own eventual deaths and transformations. You're seeing beauty and violence, creation and destruction, all happening on timescales and distance scales, almost impossible for human minds to grasp. But we can try. We can look up, we can wonder, we can use our science and mathematics to understand what we're seeing. And in doing so, we become part of the story. We become the universe's way of knowing itself. There's a quote often attributed to various philosophers and scientists. We are the universe made manifest, trying to understand itself. Whether or not anyone actually said those exact words, the sentiment captures something profound. We are not observers looking at the universe from outside. We are part of it. We are the universe, examining its own nature, marveling at its own beauty, asking questions about its own origins and fate. And that realization, that deep understanding of our place in the cosmos, is perhaps the greatest gift that astronomy can give us. Not just knowledge, though the knowledge is fascinating, but perspective, humility, wonder. The sense that we're part of something much larger than ourselves, something ancient and ongoing, something that stretches from the Big Bang to the far future, from the smallest subatomic particles to the largest galaxy clusters. So as we bring this journey to a close, carry that perspective with you. Remember that you're made of stars. Remember that the elements in your body were created billions of years ago in stellar cores and scattered through space by supernovae. Remember that the same physical laws that govern stars also govern you, that you're woven into the same cosmic fabric, that you're connected to the universe in the most fundamental way possible. And maybe, just maybe, the next time you look up at the night sky, you'll see it a little differently. Not just as distant points of light, but as beacons of cosmic history, as factories forging elements, as your ancestors, in a very real sense, as fellow travelers in this vast, strange, beautiful universe we all share, as reminders that we're not alone, not isolated, but intimately connected to everything that is, was, and ever will be. The stars shine on, as they always have, as they always will, at least for billions of years more. And we shine too, briefly, brilliantly, our consciousness, a brief flicker in the long night of cosmic time. But what a precious flicker it is. What a privilege to be aware, to understand, to marvel at the universe that created us. So sleep well, knowing that you're part of this grand story. Dream deep, and perhaps your dreams will carry you among the stars, to nebulae and supernovae, to red giants and white dwarfs, to the quiet majesty of the cosmos unfolding according to laws both simple and profound. And when you wake, remember that you carry the stars within you. Always have, always will. What is a star? It's the question that brought us here. whispered softly at the beginning like a child asking where light comes from. And after wandering through nebulae and nuclear fusion, red giants and supernovae, white dwarfs and neutron stars, we find ourselves gently circling back to where we began, still wondering at the quiet majesty of these cosmic beacons. We've learned that stars are born from clouds of gas and dust, slowly collapsing under gravity until fusion ignites in their cores. We've explored how they spend billions of years fusing hydrogen into helium, shining steadily in a delicate balance between gravity's crush and fusion's push. We've discovered that when stars die, they don't simply vanish. They transform, shedding their outer layers or exploding in supernova, scattering the elements they've created through space. We've seen that the carbon in our cells, the iron in our blood, the calcium in our bones, all of it was forged in the hearts of stars billions of years ago. We've understood that we are, quite literally, made of stardust. The universe is not something separate from us. We are part of it. We are the cosmos examining itself, matter become conscious, star stuff contemplating its origins. Maybe stars aren't just celestial furnaces following predictable physical laws. Maybe they're something more, ancient storytellers, silent witnesses to the unfolding of cosmic history, patient teachers showing us where we came from and where we might be going. Maybe that's the whole point. Not to fully understand them, but to wonder at them, to let them inspire awe and curiosity and humility, to recognize in their light our own origins and our connection to everything that exists. The universe doesn't need us to understand it completely. It simply unfolds, stars being born and dying, elements being created and scattered, galaxies spinning through the darkness. We're fortunate enough to be here, in this brief moment of cosmic time, able to look up and wonder, and perhaps that's enough. So with all of this in mind, are you still awake? If you are, I hope it's not because I was too interesting. Though if I was, well, at least you've learned a few things about the life and death of stars along the way. You know now why you're made of stardust, how stars create the elements, and why supernovae are some of the most important events in the cosmos. Not bad for a sleepless night, really. Before you drift off completely, I'd love to know where you're listening from and what time it is in your part of the world. Drop a comment and share. Are you somewhere dark enough to see the stars right now, or are city lights washing them out? Are you perhaps studying astronomy, or just someone who finds the cosmos strangely soothing? If you found this gentle journey into the life and death of stars relaxing or informative, or both, please do consider giving this video a like and subscribing to Sleepy Science Student. It's a small gesture that helps me keep bringing you more calming, curious content from the world of science and beyond. And it lets me know that these quiet explorations of the cosmos are reaching minds who appreciate them. Thank you for joining me on this journey through the life and death of stars, from their gentle birth in nebulae to their spectacular deaths that seed the universe with elements. Sleep well, dream deep, and may your thoughts drift among the stars, those brilliant points of light that have watched over Earth since long before humans walked upon it. Remember, you're made of stardust. You carry the stars within you. You are the universe, conscious and wondering, connected to everything that ever was and ever will be. Good night.